Hello, welcome to the second part of this lecture series where we look through the importance and the working of Bayesian hierarchical models. Today we would learn about how the vanilla Bayesian statistics work and derive from that how Bayesian inference is built. So let's take a look at what Bayesian approach is. As you might already be aware, Bayes' theorem is the fundamental axiom for probability and statistics. And what in its essence it defines is the conditional probability of an event happening in case some other event has already happened. And this kind of situations are very common in real life applications where there is some sort of correlation between two different events, or in our case parameters, and that correlation can be then mapped to find out missing values of one of the parameters, knowing the values or the input from the other parameter. So let's take a look at how it's different from the regular frequentist statistics. As you can see, some points that are mentioned here are that this data are generated randomly. That's for the frequentist statistics. They also have different assumptions, like whether your data is Gaussian data or what's its density, things like that. But what we are really interested is that most of these points are similar for a Bayesian approach. So what's the difference? The difference is that for a Bayesian inference, you need some sort of a prior. Prior is information about what kind of uh, posterior belief you can produce from a given input. Prior can be anything from just the values of the previous output run to the statistical histogram based models that can define what would be your prediction or what would be your posterior given a certain input value. So in Bayesian inference, what we do is we take this prior belief, and along with that we take in account the current trend of the data. What are the what's the density of the data? What are the what's the mode of the data, what's the data trend in terms of the histogram, things like that. So let's take a look at how it works. So we have some examples here of Bayesian approach at solving some real life problems. So say for example, if you have P to be the proportion of women in the population, and then you randomly sample n people with replacement, then and just do a simple binary classification, that is one for women, zero for otherwise. Then the frequentist approach, we use some sort of confidence interval based on how sure we are, and this is purely statistical, it has nothing to do with probability. But in Bayesian inference, when you have a range of confidence interval, it's due to the probability of say randomly chosen x of k element from this sample, and then for them to be a woman or not in this case. So let's take a look at what's next. So this is just the example that is continued. uh, yes, so now what we also take a look at in terms of the prior distribution is the probability density function. So whenever you want to map out the values of a certain data set in terms of its input and output predictions, based on some sort of a model or some sort of statistics, you can always create a prior distribution. And what it tells you is the prior distribution here is based on probability density function. And what a probability density function tells you is, if you have a certain uh, a certain input parameter, then what are the different probabilities that it has, but also what are the chances of getting that certain output. So it's not only just the probability, but the likelihood of each of the probability values. So let's move on to the next page and see how. So here some formulas are given. It states that the base formula, when extended, goes like this: x1 to x of n. You might have only learned about theta given that x of 1 or x of 2, but using just simple linear algebra, you can extend the equation to n number of input parameters or dimensions. Now, theta is an independent vector here. Sorry, theta is an independent constant here, and it's not effective on the different values of x. And in moving ahead, uh, yeah, this is something quite important. So there are two types of priors. Like generally, we have informative priors, which tell us about what the data set trends are. Now, what if the data set that you are working on has no previous training, or it has errors or incorrect parameters that you changed and now cannot trust the original prior? So in that case, you lack the informative prior, and then the class of the prior becomes non-informative prior. It's uh, it's not generally advisable to go for non-informative priors, but you can sort it out case by case. There are two ways to understand priors, that is, whether it is bounded or unbounded. And what does it mean is that it's just as simple as that: is there a constant probability density function available for your given prior? If it is, and if it's uniform, then you can say it's a bounded. But if it's not proper PDF, such as, for example, your probability density function tapers off in the middle of the trend, or it does not create a perfect shape, then that could be counted as an unbounded. But most of the values on your data set are not mapped into the probability density function. So that would be an unbounded prior, and it's not generally advisable to trust the unbounded priors. Uh, you can still make posterior distribution, but it just would not be as accurate as the standards of Bayesian inference are said to be. And these are some examples of the same. Yeah, so that's about all there is to Bayesian inference. Next, we'll see how hierarchical models work and what kind of why do we call them hierarchical models essentially. So, and you can also see here that this is the Bayes estimator. So this is, let me just jump back to this. When you don't have some form of a parameter or output, you can also use Bayes theorem as an estimator to just to put in the prior and then think as if what would be the output here, or what kind of parameter could have formed this output. And that is what we call a Bayes estimator. So it's kind of trying to find out the value that we generally don't have any idea of. Um, yes, and I think that's it. Yes. So this is the citation to the website from MIT OCW. Thank you to the folks there for providing this great learning resources, and thank you for watching.